Hello, I'm Professor Steve Miller. Today, we'll be talking about Prandtl-Meyer expansion fans in an introductory fashion, which is the start of a new module. We will introduce their history, what they are physically, and of course derive their theory in one class. Then we'll discuss the all-important so-called Meyer function, which is based on, of course, viscosity. And then we'll talk about a particular solution approach for the Prandtl-Meyer problem. We'll have a series of classes on Prandtl-Meyer expansion waves, which is one of our most interesting and analytical, beautiful theories in fluid dynamics. I like to start with a quote for this particular class, and this is one from Meyer, Theodore Meyer, to, of course, his advisor, Ludwig Prandtl, in a letter dated May 5th, 1918. Reference GOAR 2647 in the Göttingen archives. He wrote to Dr. Prandtl, "It would be difficult to create the right mood under which the present circumstances, but perhaps by accident another beautiful differential equation will come along again, as it once did when I worked with you." This is in reference, of course, to the differential equation he was solving, which we'll look at today in class, for, of course, the Prandtl-Meyer expansion flow. Today, we name these types of flows after Prandtl and his student Meyer. Now, we have previously examined compression waves at great length throughout this class, which form, of course, into shock waves. A coalescence of compression waves could indeed become a shock wave in the piston. Indeed, if the piston problem in a tube moves in the other direction, then an expansion waves form, we know that they never coalesce. We'll look at this in multiple dimensions in the terms of the expansion fan, which is very much like a beautiful Japanese fan which expands out from its base. These form when supersonic flow is so called, in my terminology, as a way to remember it, the flow turns out of itself. The shock waves form when the flow turns into itself with some positive turning angle. The flow is turning into itself. When the turning angle is negative, so to speak, or a positive expansion angle, the flow turns out of itself and indeed it expands. We have actually seen many flows up to the point in this class where we observe the beautiful expansion waves of the flow. This is very much opposite of a shock wave. The expansion wave expands the flow and, of course, lowers the densities, pressures, and temperatures, while a shock wave raises them. And so in many ways, you can think of a shock wave as the opposite phenomena as the expansion wave. Let's get started and review some particular notes and properties from experiments of Prandtl-Meyer expansion waves. First, we see that through the particular expansion wave, the Mach number actually increases. So from state 1 to 2 across an expansion, or a differential element of the expansion, the Mach number is increasing. We also find that the thermodynamic properties, pressure and temperature, indeed decrease throughout the wave. So the static pressure and static temperature is decreasing. And that makes sense because, of course, the flow is expanding, just like in the divergent part of a nozzle, through, of course, a series of expansion waves. We can also see that indeed the density decreases. So the density is going down through the expansion. Now the expansion wave is a continuous region of the flow, which is unlike a shock wave, which can be seen as a very small or discontinuous or discontinuity in the flow. So expansion waves represent a continuous phenomena in the flow. It's part of the continuum of the fluids. You'll also note that if you let streamlines go through a vector field defined by the Prandtl-Meyer expansion wave, then indeed they are smooth and continuous, unlike the shock waves, which cause instantaneous changes in the directions of the streamlines if it's an oblique shock. You'll also notice through our theory and derivations and experimental observations that indeed there's isentropic flow through the expansions because, of course, the flow moves through a continuum and there's nowhere for the expansion and entropy to go. So we know through measurement in our theory, which we'll develop shortly, that the isentropic flow indeed occurs through an expansion, of course, as low as there's low turbulence intensity in the flow, which is a bit of a caveat. Now, this whole theory, shock waves and Prandtl-Meyer expansion waves was completely developed theoretically and verified through experiment by Prandtl and his group. In particular, his student Theodore Meyer did the predominant amount of it work, and he published all shockwave theory and all expansion wave theory in a single Ph.D. dissertation in 1908 under Dr. Prandtl. This dissertation was only 46 pages in length. Compare that to dissertations today, which might be a few hundred pages, maybe 150 to 200 pages typically in engineering, or even an art history or English dissertation, which might be 400 to 500 pages easily. You can see there's something to be said for conciseness and impact of a beautiful theory from a beautiful differential equation. Let's talk about the history of these two particular people. And you've seen, of course, Prandtl's name come up and mentioned many times throughout the course. Here's two historic photographs of Prandtl in the upper right and the lower right. The lower right one, of course, is a more formal picture. In his younger days, in 1904, you can see him pictured by his particular fluid channel test, which is nothing more than a water basin with a turning water wheel. Indeed, his experiments were much more complicated later on, and you can see that indeed they helped explain the flow through supersonic converging diverging nozzles after Stodola's experiments, which we discussed earlier. He was an expert in aerodynamics, transonics, the inventor and father of boundary layer theory, thin airfoil theory, lifting line theories, and the famous Prandtl-Meyer corrections, and many more theories. If you stay in this field, you will undoubtedly see his student's name and his name throughout the entire subject. He did earn his PhD in Munich, and one of his most famous papers, which started boundary layer theory, was called Fluid Flow and Very Little Friction, where he described the boundary layer. One of his students, whose focus of our whole class today, was Theodore Meyer, which we'll talk about the history of momentarily, and he indeed developed the first theories of supersonic flow and shock waves. Prandtl, Professor Prandtl, was director of the Kaiser Wilhelm Society, and as you know, Kaiser Wilhelm was a very important person in Germany, especially before World War I. Nonetheless, his doctorate students, and I list just some here, were Ackert, Blasius, Bussmann, Munk, Nicorosi, Holholsten, Schlichting, Tingens, Tolman, von Karman, Vishnu, Madhav, Gautaj, and many others. Notice another one is Theodore Meyer. He had 85 in total, and many of them went on to do amazing things. For example, Maxwell Munk, pretty much ran NASA Langley and NACA in the early 1900s. Bussmann, of course, I showed earlier in this class, invented swept wings. Blasius studied laminar boundary layers and found analytical solutions to the boundary layers. Schlichting studied turbulent boundary layers, and one of the most famous books in, of course, the field is Schlichting's and his student Gersten's boundary layer theory book. These are all amazing contributions. Another student of his was von Karman, who went off and started Jet Propulsion Lab at Caltech, which is now NASA JPL, and he was one of the leading researchers in the United States in fluid dynamics. In fact, von Karman and his advisor Prandtl did not get along later in life and were rather competitive. In fact, in 1953, Prandtl passed away and didn't see the end of World War II. I'm sure he would have been unpleased with the outcome, but as an American, I am very much pleased with the outcome. And, of course, the rise of von Karman's Institute in the Americas, which helped win World War II against the inventions of Professor Prandtl. Nonetheless, he died at Göttingen, which is the university where he practiced, on the 15th of August, 1953. Let's look at his student, Theodore Meyer. And here's one rare picture of him. This is a photograph of Theodore Meyer, which was found by one of my former professors, Gary Settles, formerly of Penn State. Here he is, pictures of an officer during World War I. This was given courtesy, of course, Christoph Meyer, one of his descendants. He lived from 1882 to 1972, far exceeding his advisor in Germany. He was born as a Lutheran in Bavesen. He wrote his PhD at 26, and it was only 46 pages long, and it contained Prandtl-Meyer expansion wave theory and shock wave theory and more for his doctorate. It was the cornerstone of the modern discipline of compressible flow, and in fact, the majority of this class. He was likely the first method of characteristics development for wind tunnel creation at the end of World War I, which we'll talk about in a few classes. We've mentioned method of characteristics, but we haven't studied it yet. Now, for World War I, he was indeed drafted for military duty as an officer, and he served in World War I as a captain in the German infantry. In fact, he received a letter and had to report to help develop, unfortunately, chemical weapons. After World War I, he was very unhappy with what he saw in the war, and he quit the profession, so to speak, and he became a school teacher. Unfortunately, he hated becoming and performing, teaching basically what we would call K-12. He hated the subject, and certainly I think he enjoyed his life very much as a researcher under Dr. Prandtl, but the war unfortunately took a huge toll on this man, especially with witnessing the advent and use of chemical weapons on the Western Front. First, we'll look at a particular Schlieren image. Here, we have a Schlieren image of a Prandtl-Meyer expansion fan, which has been isolated from the other parts of the flow. The flow moves from left to right. This almost solid color here is actually the wall. It's not a solid black. This is the wall. And this is the turbulent boundary layer on the wall where I'm moving my cursor. Here's the incoming fluid with a supersonic Mach number. The Mach number then goes through this strange phenomena here, and it goes to a higher Mach number. So this is an isentropic flow everywhere except in the boundary layer along the wall. Here's the fan, and you can see there's one almost discontinuous color, or not discontinuous, but discoloration. And here's another discoloration. And you can almost see there's a fan in here. So the fan is attached to part of the wall where the flow turns at a turning angle of some positive angle in, say, degrees. The fan attaches to where the wall turns. Let's try and analyze this problem momentarily. Let's draw a schematic of this particular Schlieren image. So from figure 300 of the slide deck, I've drawn a wall here with ticked lines, and then I've shown the beginning and ending of the fan, the flow phenomena. And I have states 1 and 2 before and after the fan. So in state 1, we have a supersonic Mach number, and we'll find that expansion fans do not exist with subsonic Mach number. And there's a static pressure and static temperature in front of the fan. After the fan, a Prandtl-Meyer expansion fan, we have another Mach number M2 and another static pressure and static temperature P2 and T2 respectively. Now we'll draw these lines and call them the forward Mach line and the rearward Mach line. In fact, we'll find that these particular Mach lines are very much related to the Mach waves, which we derived earlier in the class. And so between there's some flow phenomena happening. We also define two particular angles, mu1 and mu2. And these are what we call the angle from the forward Mach line, which is shown here in the Schlieren, and the rearward Mach line, which is the end of the fan. And so mu1 is measured from the initial flow vector direction, parallel to the wall, if you will, and the second Mach angle, or Mach line angle, is measured from after the flow direction, parallel, of course, to m2, vector m2. Now there's an angle between mu1 and mu2, and that could just be defined as their difference. And there's the final angle, which is due to the geometry. It's the flow turning angle through the expansion, which could be theta. In this case, theta sub 2 is the angle relative between the two walls, as shown in figure 301 of the slide deck. So you can see now we have a schematic diagram of the Schlieren of the most basic two-dimensional with a span Prandtl-Meyer expansion wave. Let's try and analyze this particular problem now. You'll see that these expansions indeed occur in many different places, as we've seen through this course. And they occur in jet flows, external aerodynamics, internal dynamics, and corner flows, as shown in the most basic example in figure 300. Let's analyze this problem. And it's a marching problem. So just like shock waves, where we march from upstream to downstream, we'll march from upstream to downstream, that is in the direction of the flow, if we know some particular values. Let's say we assume that we know the incoming Mach number the incoming static pressure and temperature respectively, and the flow deflection angle theta sub 2, or just theta in this case. There's only one deflection angle. That, of course, is very much just like the deflection angle of the shocks, but of course, we are turning the flow out of itself. So the changes in these flow properties can be found after the expansion if we do a marching problem, or actually some point anywhere in the expansion. For example, we could find the flow properties within the expansion too, or if between the forward Mach line and the rearward Mach line defined by mu1 and mu2. And so if we only know the properties in front of the expansion and the turning angle, we can solve the problem. So to do that, let's do it on a differential basis, just like we analyzed every other problem in this class. We'll consider a very, very, very small change in the properties across a very, very weak shock waves. And then, of course, we'll find the wave deflection angle. We'll say that instead of a whole turning angle, say like 10 or 20 degrees, we'll let that become very, very small for our analysis. That will be d theta. So our turning angle of flow will be d theta, and of course we'll have some sort of small angles d mu1 and d mu2, and we'll let a differential element occur of d theta to analyze the problem. The wave deflection angle, that is the expansion wave deflection angle, will be d theta. Let's draw this now. Here's a diagram in 302. We call this the differential changes within the Prandtl-Meyer expansion wave. Here, the wave will be defined by d theta, and we'll only analyze the results across a Mach wave, a single Mach wave with a turn. So the incoming velocity will be here, in this notation, capital V. And if there was nothing happening, it would go along a straight line, which is, of course, the dashed line. The Mach wave, which is the phenomena of the expansion, a bunch of Mach waves will become an expansion, a family of them, and they'll be drawn as a solid line. Now, there's some turning of the flow, and we know the flow might accelerate or deaccelerate. For now, let's just write the new flow velocity after the wave will be v plus dv, a differential element dv. And it'll be turned by an angle d theta. You'll notice that d theta, the turning angle of flow, is also equal to a potential turning angle of flow if there's a wall. But we're only doing this anywhere on one particular point of the wave. So of course it's a local differential element theory. We'll call the initial angle mu between the flow direction and the wave angle, which of course we've shown on the figure. There's indeed no such thing as mu1 or mu2 because there's only one Mach wave in the differential element. We can then, of course, draw a line which is perpendicular to the Mach wave and connect it to the end of the velocity vector. And through simple trigonometry, we can find all the other angles within this trigonometric system of mu theta with respect to v and v plus dv, which is dependent on d theta. Let's use this diagram to analyze the problem. And you'll notice we're only using geometry and trigonometry to analyze the problem. Fascinating. So using the law of sines, I might write u plus du over u equals sine of pi over 2 plus mu all over sine of pi over 2 minus mu minus d theta. So look, on the upper left of 527 in the slide, I have u plus du over u, and on the right I have sine of theta over 2 plus u all over sine pi over 2 minus mu minus d theta. Look at that and see if you can derive it, where v is u in this case, from the diagram yourself. Take a few seconds to try and do that. Remember, our goal is to find the relations of changes in velocities with, of course, mu and theta. So now we have an equation where we're relating u and du, the ratio of the changes across the Mach wave, with only a function of the turning angle d theta and, of course, the Mach angle mu. Now look very, very carefully at the equation 527. In the numerator, we have a sine of pi over 2 plus mu and a sine of pi over 2 minus mu minus d theta. Let's use particular trigonometric identities to simplify the numerator and denominator of 527. We'll say the sine of pi over 2 plus mu goes as sine over pi over 2 minus mu, which is indeed cosine of mu. We can do the same trigonometric identity, but using a variable substitution of mu minus d theta for mu, and we can write it out as cosine of mu plus d theta, just like 528, right here and here. And then we can expand this with another trigonometric identity as cosine mu cosine d theta minus sine mu sine d theta. Now, we'll substitute these two trigonometric identities into 527 and simplify. We'll now have 1 plus du over u, which is the rewritten form of 527, u over u plus du over u, that's 1 plus du over u, which is equal to the right-hand side simplification from our trig identities. That's cosine mu all over cosine mu plus cosine d theta minus sine mu sine d theta. You'll very much note now that d theta is small, and now, because of the small angle assumption, we can write d theta goes as d theta and cosine of d theta is 1. Why? Because of course sine of a very, very small value is approximately its very, very small value, and the cosine of a very, very, very small value, like say epsilon or d theta in this case, a very small differential element, will be about 1. We can now substitute the small angle assumptions for small angle, 531 and 530, and simplify, and we can write 532, which is 1 plus du over u, which is the left-hand side of 530, which will go as, after simplification, as 1 all over 1 minus d theta tangent mu. Now, recall the series expansion as Theodore Meyer did in his Ph.D. dissertation. If you remember that from Calculus 2, we can write out 1 over 1 minus x goes as 1 plus x squared plus x cubed, a beautiful series expansion. We can also look at our previous equation, and we can expand it in a similar form. Just like 1 over 1 minus x, we might expand 1 plus du over u as 1 plus d theta tan mu plus additional terms. But we'll cross out these additional terms because, of course, we're dealing with d theta tan mu squared, which will be very, 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 very small values relative to the first order and zero order terms, 1 plus d theta. So we've done a linearization, but that's perfectly okay because, of course, we're doing a differential element type approach. Now, we'll also note that d theta can be approximated as du over u all over tan mu, and we previously derived the Mach angle relation of mu equals arc sine of 1 over m, and we can write these two equations now as tan mu goes as 1 over the square root of m squared minus 1, where square root of m squared minus 1 is the off-design parameter beta of the flow. Note that m, of course, here, because we're supersonic, should indeed be greater than 1. Therefore, the square root is greater than 1. Now, we'll substitute this relation, tan mu of 1 over square root of m squared minus 1, relation into the d theta relation, which we previously developed, right here, and substitute back in, and we'll find equation 535. Indeed, we'll find d theta equals the square root of m squared minus 1 du over u. This is indeed the governing differential equation for Prandtl-Meyer flow, and I've boxed it because it's so important. What does this equation say? It says that d theta, the small flow deflection angle, the change in the flow direction through an expansion of a differential expansion, goes as the square root of m squared minus 1, and of course you know that m has to be positive here, times du over u. Now let's say that indeed m squared was less than 1, or m was less than 1, say it's 0.5. We would have 0.5 squared minus 1, which would unfortunately be a negative square root. And so we would not be able to take and formulate this equation the way we defined it. And so therefore you can see for this equation to be valid, we must have m greater than 1. For the signs on the left and right side of the equation to be true. And so the equation physically means that if we have a small deflection angle, then of course the first term on the right hand side will be just above 1. Then therefore du over u means we have a slight increase in the flow velocity. A small change with respect to the initial velocity u. Let's make observations which I just noted. Remember, an approximate equation for d theta will be exact as we let the limit of d theta go to 0. We derived this equation only based on geometry and trigonometry of the flow problem. We made no assumptions on the gas if it's perfect, real, or even chemically reacting. So the Prandtl-Meyer expansion relation will absolutely be valid in the differential form for perfect gases, real gases, or even flows with chemical reactions. Unfortunately, this differential relation, which I boxed the Prandtl-Meyer differential relation, is only valid for small angles of d theta. But in reality, we turn through finite positive turning angles. And so we need to extend our analysis now to positive finite turning angles to solve practical problems. How do we do that? With an integral approach. If I integrate the left and right hand sides of 535 through the turning angle and through Mach numbers, I arrive at the famous equation 536, which is also shown in in Theodore Meyer's dissertation. We'll integrate the left-hand side differential from theta 1 to theta 2. That's the angle, that's through the entire angle of course, the flow deflection, will be equal to the integral over Mach number from m1 to m2. Now, if we're able to integrate this equation, then we can know du and u in terms of m, right? So we have to somehow find du over u in terms of m to evaluate 536. So we'll choose, it's our choice, to perform the natural log operation on u, and we can write it out as, using our speed of sound definition, m equals u over c, as the natural log of u goes the natural log of m plus the natural log of c. We can then differentiate 537, which will be du over u will be equal to dm over m plus dc over c. Try these operations yourself. Now recall the adiabatic energy equation as a function of stagnation, speed of sound c, and static speed of sound c, which we previously developed in this class. So in 539, we have t naught over t equals 1 plus gamma minus 1 over 2 m squared. These two terms represent, of course, the isentropic relation, which we developed in our isentropic module between stagnation temperature and static temperature, and 1 plus gamma minus 1 over 2 m squared. So for a given Mach number, we have a static temperature, and if we let the flow isentropically deaccelerate, we'll get a stagnation temperature T naught. Using C equals the square root of gamma RT, where gamma and R are constant, we can write this equation as C naught squared over C squared equals T naught over T. And therefore, we have the adiabatic relation between stagnation speed of sound C and static speed of sound C. Now, we can solve 539 for C, and we'll have C equals C naught times 1 plus gamma minus 1 over 2 m squared to the negative 1/2 power. We then differentiate with respect to C, and we'll have dc over C from the left-hand side of 540 goes as the differentiation on the right-hand side will go as negative gamma minus 1 over 2 m times 1 plus gamma minus 1 over 2 m squared to the inverse power times dm. We can then substitute dc over C, 541, into our differential equation 538, du over u, dm over m, plus dc over c. So the most right-hand side term, and simplifying, will give us du over u goes as 1 over 1 plus gamma minus 1 over 2 m squared times dm over m. And remember, we're applying this to each differential element within the integral of 536. So you see in 536, I've done this operation so I can replace du over u, which is now only a function of m and dm over m. And so of course our integral in 536 will only be function of m and gamma, where gamma is a constant. And so now the right-hand side of that integral, through this particular isentropic assumption for each differential element, will of course give us a way to move forward and integrate the equation. So now indeed we know du over u as a function of m only. And so we can substitute, and we'll have, after the substitution, 543, which is the integral from theta 1 to theta 2, the angles of the turn, d theta, will be equal to theta 2 minus 0, and we choose simply, of course, theta 1 to be 0. It's our choice, and so we only have one turning angle, theta 2. And that's why in the diagram previously shown in this class, I've labeled this as theta 2. So we have theta 2 now equals the integral from m1 to m2 of the square root of m squared minus 1 over 1 plus gamma minus 1 over 2 m squared times dm over m. Now we'll let and define a new function, nu, and we'll call nu, which is only a function of Mach number, equal to the integral on the right-hand side of 543, which we put on 544. This is what we call the Prandtl-Meyer function, nu, which is only a function of Mach number, as you see through the integral relation, integrated from m1 to m2. This integration can be done analytically, and is the whole reason we went through this mathematical process, through many trials and error done through the hard work of course, Dr. Theodore Meyer's effort. Here I've boxed the analytical integration of 544 into 545, which is also shown in your equation sheets. We'll have the Prandtl-Meyer function nu as a function of m goes as the square root of gamma plus 1 over gamma minus 1 times arctan of square root of gamma minus 1 over gamma plus 1 times m squared minus 1, all minus the arctan of square root of m squared minus 1. So indeed, we'll let the integration constant be 0 from 544. What does that mean? It means that by letting the integration constant, lower bound m1, mean that our turning angle will of course be 0, or defined as m equals 1. That means for theta 2, we'll define a very important equation, which I haven't boxed here, but you should memorize it, and it's also on your charts, as theta 2 equals the Prandtl-Meyer expansion of m2 minus the Prandtl-Meyer expansion of m1. So that means the turning angle of the flow is equal to the difference of the Prandtl-Meyer functions, nu m2 minus nu m1. So therefore, we can tabulate this Prandtl-Meyer function in the tables for different values of gamma with respect to particular Prandtl-Meyer functions. So how do we use this equation as a tool to solve problems? And I'll describe the steps here, and we'll show some examples in class and through homework, and of course it'll appear on tests and midterms. Step 1, we would seek the Prandtl-Meyer function at m1 from a table for a given Mach number. For example, if our incoming Mach number is 1.5, we would look up m1 1.5 in the table and look up the corresponding value of the Prandtl-Meyer function. Or we could put m in this right-hand side of 545 and solve for, of course, the Prandtl-Meyer function and label it nu sub m1. The second step would be to calculate nu sub 2 from the equation theta 2 equals the differences of the Prandtl-Meyer function after and before the fan, respectively, from particular angle theta 2. And so we would know the turning angle theta 2, the expansion angle, the flow angle which the flow deflects, and we know already nu m1, which is the Prandtl-Meyer function. So we can solve for nu m2. So that means we can now know nu m2, and we would once again use 545, and we know the left-hand side nu m2, and we can solve for m2. Now we know the Mach number after the fan, which is step 3. Now we've made the assumption to find the Prandtl-Meyer expansion equation function in 545 that's isentropic. Therefore, we can use all our previous isentropic relations to find the new static pressures, temperatures, and densities behind the fan, because we know indeed that the total pressure and total temperature and total density and total speed of sound are all constant on a particular streamline through the fan. And so you can use normal isentropic theory to cross the fan once you find m2 through traditional theory. These functions are listed and tabulated in our traditional charts. Here you'll see the famous Ames tables in the supersonic flow section of isentropics. Of course, it's an isentropic flow phenomena, so these should look familiar to you. We've also listed these very same tables, of course, in the class handout in a little bit different form, and we'll also explain those. Once again, the first column is m or m1. We've listed particular very large Mach numbers from 55 to 100. For a given Mach number, you can go across each row of the table and find a particular value nu, which is shown in this column. This is a value in degrees and represents, of course, the evaluation for any given Mach number, the particular Prandtl-Meyer expansion fan listed here. So 545, the evaluation equation 545 with right-hand side Mach number is evaluated for left-hand side Prandtl-Meyer function. So here's the left-hand side of 545, the Prandtl-Meyer function equation, and here's the right-hand side in terms of Mach number. So they've put these values in a table. So you can easily find M1 and find the Prandtl-Meyer expansion function. And then, of course, find the appropriate turning angle and new Prandtl-Meyer function as a function of M2. And then look that up later in the column, which will always be below the first value you look up if you're moving downstream, and go across and find the new Mach number. Because of course Mach number must increase through the expansion, as we showed and proved mathematically through our analysis with the differential form of the Prandtl-Meyer function. Let's look at, of course, Theodore Meyer's original diagrams of the beautiful Prandtl-Meyer expansion. This is as shown in 304 of the particular slide deck of this class. And he shows two particular figures here. The lower figure is his original diagram and analysis of the oblique shock wave. Take a few minutes and appreciate his notation, which is very much similar to the notation we use today. You can see, indeed, he put a control volume across the differential element just like we did in oblique shock wave theory. So unbeknownst to yourselves up to this point, we have actually repeated exactly Theodore Meyer's oblique shock wave theory calculations. In the upper figure, in part A, he shows a particular stream tube being bent through a turning angle where he has drawn the fan, which is the exact same turning angles here and here, side 1 and side 2, and exact same angles and expansion which we used to find the differential element, which he did just like we did in this class. So it's very interesting. You can appreciate to look at the original drawings of Theodore Meyer, which derived this beautiful theory. Now, in Theodore Meyer's dissertation, he actually also made these particular oblique shock polar plots. This is probably one of the original types of oblique shock wave plots, because of course he found the theory of shock waves for these particular problems. Here, in this particular case, on the y-axis, he has a pressure ratio P1 over P naught before the shock, which is plotted as P2 over P naught after the shock. Once again, with particular flow turning angles, which are the family of contours and solutions on the plot, are shown, which make these beautiful shock polars. So it's a different type of shock polar diagram, but it's not very useful relative to working fluid dynamics, which we do today. This is why we don't typically draw shock polars this way, because they're just not as practical for solving problems. Now, here's two more images from Theodore Meyer's original 46-page dissertation. In the top, in part A, he has solutions for the streamlines with constant velocity and transonic flow within a de Laval nozzle throat, which he has shown in a Schlieren image from Dr. Prandtl's lab, where you can see particular Mach lines in the flow. Now, this is designed with the method of characteristics, which we'll talk about in a few classes. A method of characteristics nozzle operating isotropically has no shock waves, but it does have a system of Prandtl-Meyer expansion waves. The Prandtl-Meyer expansion waves, or Mach waves, a system of Mach lines or Mach waves, which we talked about earlier and derived this theory, can be seen as this crossed net. You see almost like a crosshatch pattern. And so you can see along the upper wall and lower wall, indeed, the flow is turning out of itself, and the flow is expanding from the transonic condition here, which is a quadratic relation for the sonic condition, and expands from left to right and accelerates supersonically. Each one of these little differential elements on the wall represents a turning angle, which the flow is turning out of itself, and the flow is accelerating. These are all creating Mach waves or characteristic waves, which form expansion fans, which can be found and dictated by the theory we derived in this class. The upper figure shows his graphic of the de Laval nozzle and particular streamlines, which are the solid lines. Here's the center line of the axis, through that transonic section. You can see it also forms a characteristic net, which is exactly correspondent to the characteristic net which he saw in the Schlieren images. It was a work of true genius. Indeed, he was the hidden genius and perhaps true father of compressible flow theory, which we're learning in this class. In this class, we introduced an all-new subject of Prandtl-Meyer expansion fans. We looked at the physics of them and their history of their creators, which came out of Germany. Then we looked at the theoretical developments of Theodore Meyer in a historical context and reviewed his Ph.D. dissertation. Most importantly, we derived the Prandtl-Meyer function, nu, which we just call informally the Meyer function, nu, which is only a function of m. By replacing m with m1 or m2 respectively and crossing the wave through an integration with, of course, the stagnation speed of sound relation, we can find the equation as the turning angle minus the differences of the Prandtl-Meyer function expansion from m2 to m1. That is state 2 to state 1. And we show the basics of the solution approach. We'll show examples soon and more about how this theory combined with isentropic theory and shock theory to solve even more complicated aerospace problems. Thank you very much for your time today. I'm Professor Steve Miller.